look at the effect that the dynamic load has on the E value, that elastic modulus, and see how the elastic modulus is influenced by the dynamic nature of the load. Because you start with something that is stiffer, and as time goes by, you get the stiffness starts to reduce, you get something a little softer, so then your settlements increase. Yeah.
It's a little off the topic, but earlier in the handout we were kind of differentiating between circular and rectangular foundations. In this instance, is this only applicable to rectangular foundations, or is like B the diameter of circular?
That's a good question. So can you spot one of those factors in the set of factors that are listed on this page that would take care of that?
If you eliminate
your L over.
yeah.
Shape factor.
This one, shape factor.
Right.
So this thing will take care of all those. Whether if it's a circular foundation, then L and B are equal.
Right.
So then you just plug L equal to N in this equation. If it's a rectangular, depending on what L and B is, you plug it in there. And if it's a straight footing, L over B is pretty large, so then you end up with 1.55. So the beauty of this equation is that it's very practical, and it takes care of all the different shapes of foundations that we might encounter. Any other question? All right, so now I want to add a bullet point here. For immediate cases, it's a little unclear at t equal to 0 what to input here. Because if you use this equation, if you put t equal to 0, then log of 0 becomes, what is it, negative infinity, right? So it messes up the equation. So for immediate cases, f of t is just 1. All right. Now let's go to page 14 and look at the note on SPTN values. This is something that most of you have already seen. Those of you who started working on the homework, you saw that in the Excel file. You have to decide whether if a correction needs to be applied or not. So if you have a silty sand or silts below the water table, your measured N value will be corrected based on those two equations. If you have a gravelly sand, you increase the measured N value again by this equation. So nothing really special about that. And then we get to this example here. So this example, it's an office building. Assume normally consolidated sand. It's a Holocene sand. It hasn't been loaded before. There's no geology. There's no reason to assume that based on the geology of the region, this sand was over-consolidated. And we want to find the settlement at or after 30 years, or at 30 years from the construction of the building. And it looks like this. So QB is 2 KSF. The dimensions of the building are 40, or the dimensions of the foundations is 45 by 75 feet. So would this be considered a single footing or a mat foundation? If the entire building is sitting here,
The mat.
going back to here. So single footing is when you have a small footing, 2 meters by 3 meters, and then the column sits on top of that. Mat foundation is when you cover the entire building area with a thick concrete foundation, and all the columns are sitting on top of it. So this case here, where you have a foundation that is 45 feet by 75 feet, that's a mat foundation. Okay. Okay, so that's a mat there. The depth of embedment is called D, and the question is divided into 3 sections. Part A is no basement, so the base of the mat foundation is at the ground surface. In this case, D equals 0. Case B is when you have two basements, so assuming that each basement is 12 feet tall, your D is 24 feet. And case C is one basement where D is 12 feet. Okay. So let's go back to case A. The contractors have done the boring logs, the SPT blow counts are in, N60 versus depth. They kind of hover around 20, and then at depth 50, they start increasing to something higher. So, for a case of no basement, ZF0, you plug in all the numbers, you get 26 feet. FL is a deep sand, so you get FL of 1. Pick N60 bar along the depth of influence. So depth of influence is 26 feet. So from this point down to 26 feet is around here. What is the average N60 around that, along that 26 feet? 20. Just 20, right. So your N60 bar is 20, you plug it into I/C, it gives you the value. Shape factor, you plug in L and B, you get 1.2. Time factor, assume that it's a static loading, it's an office building, we assume that it's static load. And you plug in all those numbers, you get 1.5. And then you plug them all into this, the equation. And which equation, which one of those three equations are we using here?
NC.
It's an NC, it's a normal consolidated. That's because the problem statement said that it says, assume that it's an NC plate, NC sand. So you plug it in, you get 1.1 inch of settlement after 30 years. So that's a pretty typical settlement that you would expect to get from a building. Okay. Any question on this?
And that's the settlement after 30 years?
After 30 years, correct. So you can replace that FT with 1 and see how much immediate settlement you get. So if the utility contractors ask you how much extra settlement you're going to get right after construction until 30 years, you would have to calculate the settlement at t equal to 0 and after 30 years, and the difference of those two will give you the differential settlement. And that's what the utility ones want to know, because they want to know if they connect the pipe, how much this pipe, how much settlement that pipe should be able to absorb after 30 years without breaking. Any question? All right, so now let's go to page 15 where we have case B and C. Case B is a two basement. D is 24 feet. And it's going to change two parameters. One is that you're going to have the average N60 that you have to calculate starts from the base of the mat foundation. So you have to go 26 feet below that to see to use that to average your N60 values. But the other difference that it makes is the type of equation that we have to use, the NC versus OC ones. So this is a case where you have to, you know your QB, and you have to calculate the sigma prime VP at ZF equal to 0. So sigma prime VP at ZF equal to 0 is the pre-consolidation stress before you start building the foundation, before excavation. So before excavating the site, how much stress that soil was experiencing? That would be 24 feet multiplied by, that's the assumption you have to make, that that's a gamma of the soil. Excuse me. 120 PCF or 0.12 KCF. You multiply that by 24, that gives you 2.88 KSF. So this point, and this is your ground surface, when you excavate the site, that load is gone. So this is excavate. And this point here was under 2.88 KSF load before you started excavation. So then you excavate, so that's your sigma prime VP at ZF equal to 0. And then you compare that to QB. What is your QB? That was 2 KSF, right? So you remove 2.88, you put back 2, you don't quite reach to what you used to be before, and that will be case, that is, which one of these that is, 2 or 3? You start OC, so you remove the soil, now you're OC. You add you add load back, but you add only 2 KSF back. You don't quite reach to your 2.88, so you remain OC. So this is case 3. So QB is 2 KSF. This guy is 2.88 KSF. And that is the OC and remains OC. So you use the equation, you get 0.4 inch of settlement. So compare that to what we calculated before, 1.1 inch versus 0.4. That's a lot smaller settlement, right? So if you have an OC sand, your settlements will be smaller. That's the point here. But let's look at case C, one basement. So D is 12. Again, you calculate sigma prime VP at ZF equal to 0. It's 12 feet multiplied by the gamma, and that gives you 1.4. So again, in this case, this is the ground surface, but you only excavate this much. So this point right here used to be under 1.44 KSF pressure. You remove that, now it's an OC soil. Then you add 2 KSF back. You pass that 1.44 and then you're pushing the soil into an NC region. So you start with OC and you end NC. That is our equation, the second equation that we have. So you have to plug it into this equation and you get slightly more settlement in this case, 0.6 inch compared to 0.4 inch here compared to 1.1 inch that we had in the previous case. Any question? No? All right, I think this is a good point to stop and take maybe a 15-minute break. So we start again at 12:45. Can someone pause that?
Is it this one?